This video goes a little more into depth about kinetic and static friction. So imagine you are pulling on a block and the force that you exert on the block is pretty small, so about this big. The surface then exerts an equally small static friction force in the opposite direction. Since these forces are equal and opposite, there's no movement or acceleration of the block. So, next let's say that you exert an even larger force on the block, but the surface still exerts an equally large static friction force pointing the opposite direction. So once again, we still have no movement of the block. Then you finally exert all of the force that you can on the block, and the maximum static friction force is exerted on the object. But your force is just slightly bigger than the static friction force, and therefore the object begins to move. So the static friction force can vary depending on the pulling force exerted on an object. So the static friction force can range from just a little bit above zero, so this would be if you're just lightly tugging on an object and it's not moving, to less than the maximum static friction force. This maximum static friction force would be the resistive force right as the slipping of the two objects begins. The equation for the maximum static friction force is equal to the coefficient of static friction multiplied by the normal force. And we have discussed before that there's also a kinetic friction when two objects are slipping past one another. This happens after the maximum static friction force is exerted on the object. Okay? And this kinetic friction force always opposes the velocity and has a similar equation to the maximum static friction force. But instead of the coefficient for static friction, we instead use the coefficient of kinetic friction. So here's a small table with some of the examples of the coefficients of friction. Notice that the coefficient from the objects on ice would be less than the objects on concrete. This intuitively makes sense because ice is more slick than concrete. So let's do an example to work with these new equations. So a skier is standing waiting to be towed by a horizontal rope. If the skier's mass is 80 kilograms, how great must the tension force be until the skier begins to move? And let's assume that the coefficient of static friction between the skis and the snow is 0.2. So here's our skier with the horizontal rope, and we know that the skier is just starting to move, so the tension force is going to equal the maximum static friction force, which is equal to the coefficient of static friction multiplied by the normal force. We already are given the coefficient of static friction, so we must find the normal force. To find the normal force, we need to apply Newton's second law to this problem. So we know that the skier has a normal force acting up and a weight force acting down. The skier is also not accelerating in the y direction. So we're going to say that the acceleration in the y direction is 0, and this means that the normal force acting up is equal to the weight force acting down, the magnitude at least. So the skier is also, great. Normal force equals the weight force. So we also know that weight is equal to mass times gravity, and then we can plug in the mass, which is 80 kilograms, and gravity is 10, so we find that the normal force is 800 newtons. Great, so let's plug this into our tension equation. So we have our coefficient of static friction is 0.2, and the normal force is 800, and we find that the tension force is then 116 newtons.